So we're gonna slowly get started while people are walking in. I'm Kostas. Welcome everyone to Flink Forward 2016 in Berlin. This is the second edition of Flink Forward. Let me start by what everybody wants to know first. The Wi-Fi is Flink Forward 2016. In this room, it's called Keynote Flink Forward 2016, and the password is #FlinkForward16 for both Wi-Fis. If you're tweeting, our Twitter handle is Flink Forward, and our hashtag for this year is FF16. Following the tradition from last year, we will go out and take a group photo. It's sunny today, so it's going to be nice. That's at 3:30. If you are unsure which talk you would like to go to during the conference, don't worry, all the talks are going to be recorded, and they will be made available afterwards in YouTube in the Apache Flink Berlin channel. And today, right after the conference at 6 o'clock, we have our Flink Fest, so there's beer, etc. Please keep in mind that we had some very last-minute changes to the program. The program that is online is the correct one. The program that you have printed might actually still be the old one. So the best would be to look at the program on the website. Where we are, so we are now in these rooms, the blue rooms up there. This is Keynote 3 and 6. Keynote means cinema. We're going to use this room only for the plenary sessions. This is Keynote 3. There will be talks in Keynote 6. There will be also talks in Maschinenhaus and Kesselhaus. These are when you go out to the courtyard, basically where you went for the registration and follow the signs. And the Palais, which is the place that you probably got coffee this morning, is what we will use for meals, and this is also the booth expo area. I would like to thank our sponsors for this year, so our platinum sponsors, Alibaba, Intel, and the Google Cloud Platform, our golden sponsor, Huawei, and our silver sponsors, Mapar, the Unbelievable Machine Company, and New Yorker. So please, one applause for our sponsors. I have more people to thank. So this is our program committee. These folks reviewed every submission to the conference and made sure that we have this amazing lineup for this year. It's Tyler Akidau from Google and Apache Beam, Stephan Ewen, who will get on stage right after me, Jamie Greer from Data Artisans, Vasya Kalavri from KDH, and Neha Narkhede from Confluent. Last but not least, this conference would be nothing without you folks that are here to speak and you folks that are here to attend. So a big thanks to our speakers for this year. These are most of them in photos, so thank you very much. And these are actually all the companies and affiliations from all the speakers. So these folks actually have traveled from as near as Germany and as far as the west coast of the US and China. So again, thank you very much for coming to speak at this conference. Now, for the main talk. So what me and Stephan would like to talk to you about today is how we see the broader data streaming and big data ecosystem evolving. What are the trends? What are people using stream technology for? And where exactly does Flink fit into this picture now? And what is our idea of where Flink should go in the future? So first of all, who are we? We are Data Artisans. Data Artisans is a company that was founded by the original creators of Flink. I remember writing the incubator proposal for Flink. It was not even called Flink back then. And our goal is really to make stream processing and data streaming accessible to the enterprise. And to that end, we are 100% committed to the open source Apache Flink community. We are trying to provide all the events to help this community meet and grow, for example, like this one. And we are also working together with a lot of large-scale users of Flink. And in that way, we're sort of in the middle, so we're getting a lot of experiences from different users and different companies. And this is part of what we would like to talk to you about today, so how people are using Flink. Now, if you were here last year, the first phrase in this slide up there is, streaming is the biggest change in data infrastructure. This is basically what I had used for my opening slides last year. And back then, I thought that this was a bold statement. Yeah? So it turns out that reality was actually bolder. Yeah? So unless you've been living under a rock for the last year, you might have noticed that data streaming is the big thing in big data, and it's not just a promising direction anymore. It is actually a market category of its own that is growing and maturing very, very, very rapidly. And the Flink community has actually been, during the last year, at the center of this transformation, and it was extremely influential for this transformation. And of course, we're not alone. So the Kafka community has done an incredible job in providing the message transport layer for data streams. The Flink community has pushed the envelope very much into how do you do stream processing, yeah? What can you do with streams? And more recently, the Apache Beam community has been very influential in answering the question, how should one think when programming against data streams? So there is innovation, but there is also maturation and convergence in all parts of the stack. Now, I will talk to you a bit about what are people doing with streaming, why are companies adopting streaming technology, and there are many different angles from which folks are approaching streaming. However, if you dig deep down into it, the reason that streaming is becoming popular is really, really simple, right? So most data sets, and especially data sets that fall within this big data realm, are data sets that are continuously produced. Yeah? They are often in the form of time series. They are produced continuously. They arrive continuously. And it just makes sense to process and analyze this data continuously. It makes sense to build applications that are live 24/7, continuously ingest this data, and continuously provide results. Now, as I said, there are many different angles from which folks are adopting data streaming, and these are some of the most prominent ones that we see at Data Artisans. So first, lots of companies, it is becoming extremely important for many companies to be able to monitor the business in real time and provide real-time products, demand-based products, and create alerts from this monitoring. So really understanding what are my users doing right now and understanding that continuously. That is one angle. Another angle comes from folks that have been writing applications that I call here continuous applications. These are applications that run 24/7, and they often power live systems. So before, people were writing those using a mix of libraries, using message queues, using plain Java. Maybe they were taking care of fault tolerance themselves. So it was a wild mix of things. Or maybe they were writing these applications using repeated Hadoop jobs. Now, streaming technology is actually the best compute framework to implement these 24/7 applications robustly. It just gives you all the building blocks that you need to implement these applications well. A third angle is companies that are actually adopting a more microservices-based architecture and organization. Yeah. So many companies are doing that right now, and when you have microservices, each team is responsible for the whole stack of an application, and when you look at this kind of architecture and you think, how do I implement the data infrastructure, the data layer that connects these microservices, the most natural way to do it is by using data streaming that pumps data between these microservices, and then the microservices are building local state based on the event streams they ingest. And finally, there is a real need to unify what people call now real-time data or transient data and what people call historical data. And streaming technology is actually the best starting point to unify these two. So these are different angles from which companies are adopting streaming. What are folks actually doing with streaming? So these companies here are companies that are either using Flink in production already, or they are exploring Flink at very large scale. And they come from a wide variety of industries. Yeah? So if you look, for example, at retail and e-commerce, it is increasingly important when you make product recommendations to take into account the latest, the real-time information. And you will actually see a talk by Alibaba in this conference that talks about that. Things like business process monitoring, inventory management, etc., very important for retail. In finance, the world of finance is changing, and banks are trying to differentiate from each other via technology, not via the best interest rate. Yeah. So for finance companies, it is doing things in real time and providing things like real-time products is very important. For example, imagine if you're traveling to a different country, right? You would very much like, when you arrive, to know if your card is locked or unlocked, so you wouldn't have to call, and you would like to know, you would like to get a map with the closest ATMs. So things like that becoming very important. Other more classical use cases in finance are things like doing very good fraud detection and even fraud prevention. In the whole telco space and IoT and general infrastructure, it is extremely important to monitor this infrastructure in real time and be able to generate alerts, so detect anomalies and generate an alert when something was wrong. So you might remember Bouygues Telecom. They were here last year as well. They're the third largest telecom in France. They are using Flink for many things, including this purpose. And finally, for internet and mobile, it is extremely important to be able to analyze what your users are doing right now and use this data to build better products, to iterate on your product, and to personalize the view that its user has for this product. So you will hear, for example, in this conference a talk by King that is around how do we get all the data from mobile games and do analytics on this data. And what is also amazing is the scale with which folks have been deploying Flink lately. So for example, the system that Alibaba has built that is based on Flink is running at a cluster of 1,000 nodes, so that's a tremendous scale. Their largest job has more than 20 operators, and it's using 5,000 virtual cores. And this job alone is processing millions of events per second. King is deploying jobs that have more than 30 operators, including operators that look up data from external databases, join streams with each other, so the complexity is actually pretty amazing. These jobs are running 24/7. They're processing 30 billion events daily, and these are actually stateful applications that maintain hundreds of gigabytes of state while maintaining exactly one's guarantees. So I think that's actually pretty amazing. And Bouygues, that I mentioned before, Bouygues has been one of the first users of Apache Flink, and by now they have been using Flink in production for more than a year, and they have about 30 Flink applications deployed and running 24/7, processing 10 billion events per day. Yeah. So my point, so streaming is maturing. Streaming is maturing both from a technology perspective and from a use case perspective. And the next question is, what is Flink's role in the streaming ecosystem? What does Flink bring to the table? Well, in my mind, if I had to summarize that in a couple of slides, it would be the following. So before Flink, users of stream processing frameworks had to make hard choices and navigate trade-offs between volume, latency, and accuracy. Yeah? So volume is how big is the input that I can process, how many events per second. Latency is how fast can I get my result, and accuracy is how accurate is my result in the case of failures or in the case of other things that are happening daily. Yeah? So before Flink, users of stream processing frameworks had to either choose frameworks that could support high volume but not low latency, or low latency but not high volume, and accuracy was always a question to be asked, so it was pretty complicated. So what I think that Flink's unique contribution to the industry was exactly the fact that it eliminates these trade-offs. And I believe this is one of the biggest reasons of Flink getting adopted so fast during the last year. So with Flink, it has been demonstrated to support tens of millions of events per second for stateful applications. That was in a very small cluster, so you can very efficiently process millions of events per second, and it has also been demonstrated to scale to very large clusters. You can get sub-second latency, you can get your latency as low as single-digit milliseconds, and you can get accurate computation results. Yeah. So I would like actually to take a moment and talk a little bit more about accuracy. So when people usually talk about accuracy in the context of stream processing, they talk about what are my guarantees when a node fails. Yeah. So I think that this is totally fine, of course, and this should be there, but it's kind of a restricted notion of accuracy because it really comes from technology. It does not come from the user perspective. So in my mind, we actually need a broader definition of accuracy. And the best one that we could come up with is accuracy is the results that I want when I want them. So this is in fact taken from a book that I wrote together with Ellen Friedman, who's actually here in the audience. It is available. It's an O'Reilly book, Introduction to Apache Flink, and you can actually download it for free from the website of Mapar. So when we talk about accuracy, of course, the first thing is that the results should be accurate under failures, right? Failures are, for me, unplanned downtime. So the next thing is that results should be accurate also under planned downtime. So when I'm migrating to a different cluster, when I want to change something on my job, when I want to migrate the framework, the results should actually be accurate then. Second, results should be accurate, or at least we should be able to control this accuracy when the input streams are out of order and when the input streams have late elements. Number three, and that is actually extremely important in the case of stream processing, right? The results, the usefulness of the results is very correlated to the time that you get them. So for example, imagine that you are getting driving directions and your driving directions in your phone come 10 minutes later. That's probably pretty useless. So there should be mechanisms to get results when you need them. And number four, one aspect of accuracy is what are the building blocks that the framework gives you to model your world as a user. So for example, imagine that you are tracking the activity of users in your website. Yeah? Your users behave in sessions, with sessions do not have fixed duration. So instead of trying to fit your problem to what the framework can offer you, the framework should actually give you the building blocks to express your problem concisely. And Flink does exactly all these four. So Flink pioneered this notion of checkpoints and save points that guarantee accuracy under failures and downtime exactly once, guarantees. Flink has support for event time and watermarks that gives you means to control accuracy under out-of-order streams and under late elements. Flink has a mechanism of triggers, which coupled with the ability to deliver results with low latency gives you as a user the ability to get results when you need them. And finally, Flink has a very flexible windowing mechanism where you can actually define windows and groupings that fit in your problem domain rather to trying to adapt your problem domain to the framework. So Flink brought the combination of all of these, high throughput, the ability to handle streams of large volume, low latency, and a broader notion of accuracy, but it actually goes well beyond that. So Flink is best known as a stream processing system. Well, you also get a batch processor when you download Flink, so you can actually analyze your streaming data and your historical data with one system. In stream processing use cases, real-time data is just one kind of data that people want to analyze. More often than not, you want to go back in time and reprocess streams, and Flink provides you exactly the ability to do that very well. And the reason is that you can do that very fast, so you can fast forward through the past due to the support for high throughput. event time support, and this notion of save point. So in Flink, you can literally reprocess a stream by typing Flink -s, resume from save point, this job. Of course, a very large ecosystem around the project, so connectors to all sorts of databases, message queues, file systems, and a lot of third-party libraries that are built on top or around Flink. And one of the most active communities in the big data world, which now counts more than 200 contributors, and meetups, Flink user groups in almost every continent on the planet. So Flink is awesome, but are we done, right? So what is next? What are the next steps for Flink? So I will invite Stephan to the stage. He will expand on all of these points, but in my view, the situation kind of looks like that. So what the Flink community managed to do during the last year with the latest 3 releases is really provide state-of-the-art stream processing capabilities that cannot be matched by anything else. The next steps, some things that we're actively working on, is make Flink be operational in production in some of the largest clusters and largest infrastructures in this world. Another thing is to open up streaming data and Flink to a broader set of users than the ones that can actually use stream processing right now. And finally, a last goal is to broaden the scope of stream processing well beyond the use cases that are now considered mainstream for stream processing. And this involves broadening the scope of stream processing well beyond real-time data. So with that, I will invite Stephan to the stage, and he will actually go in a lot more detail about what we are working on with Flink and what's the situation now and what's coming up next.
All right, thanks, Kostas. Yeah, as Kostas said it, Flink has also, in my opinion, provided pretty state-of-the-art stream processing capabilities, and I think we can sort of proudly say this as a Flink community as a whole, as everybody who has worked on that over the last year, Flink was a project that has pushed the boundaries of stream processing and came up with a lot of either new features or new combinations of features that actually allow you to do things in stream processing that people thought before were either supposed to be batch jobs or they would need custom solutions for, or when just not yet feasible in the realm of stream processing. And if we look back a year, what happened between last Flink Forward and this Flink Forward? What were the features that came up in Flink? Mainly in the releases 0.10, which was shortly after last Flink Forward, and 1.0, beginning of this year. There were a lot of features, many around the area that Kostas outlined: throughput, latency, accuracy. I have a few more details here on that slide than those 3 categories, and there's an amazing amount of pretty tough features in there. I like to classify them in these 4 areas: performance, support for sophisticated time semantics, event time, support for stateful stream processing, and just the APIs and libraries that you need in order to model the problems that you have properly and to model them elegantly and easily. And well, that was all the features that the Flink community has worked on over the last year. Let's look a little bit of what is happening right now and see if we can if we can identify a trend, sort of where things are going. So let's look at Flink 1.1, which came out recently. This is from the release notes of Flink 1.1, let's say the broader new features, not all the details that were fixed, but the broad categories in which the community added features. Connectors, metric system, so you can actually observe what is happening inside the system. First version of SQL and Stream SQL, session windows, and additional library enhancement to the graph analysis library, to the complex event processing library. And if we actually add to those that were just recently released, all those things that are actually being worked on right now. It's actually, it's a whole lot if you see that. One thing that you can say about the Flink community is that they're keeping busy. There's so many things that so many threads that are currently going on that people from Data Artisans and all the other contributors are working on. That to try and make sense of where things are going, I try to cluster it in four categories. What are kind of the problem areas where these features are trying to push the system to. And what you can see actually is that the biggest area that people are currently working on new features is actually operations. It's no longer application features, which I think was the dominant area where features were added over the last year. And there's an entire new category of features coming up that, like Kostas also mentioned, broaden the audience of stream processing. That means features that don't really allow you to build different types of applications than you used to build before. It's just tools to have different people, to allow different people to build these kind of applications. So, for example, the most obvious representative of that area is SQL and streaming SQL. It doesn't really come with any features that, let's say, the lower level Flink APIs wouldn't have. It would just allow a different type of person to implement streaming analytics. And yeah, as mentioned, the big focus seems to be, just observing all these threads, to work on operational features these days. And one other thing I would actually like to highlight here is this, that many of these features that we see here on the slide are not in the category of, okay, Flink got to patch some holes in its operational characteristic, but are really also like new features, new technologies, or at least new blends of technology from different areas that Flink brings into the ecosystem to actually make operations of streaming at very large scale, smoother than it is these days. And I'd like to pick a subset of these threads and actually quickly look into them. What is happening there? I cannot do the entire set of threads justice, just for the sake of time. If you're actually interested in hearing a little more about other threads here, there's going to be a talk in, I think in the next session, even after that one, called The Future of Apache Flink. And it will pick a bunch of more threads and actually talk about them in more detail. So let me look at these threads and then give sort of an idea where things are going actually beyond what the community is doing right now, beyond those threads. So one representative of what of features that the community is currently working on is this here, security and authentication. What that means is it kind of the medal has kind of two sides. First is making sure that Flink works very well in high security setups where access to all coordination and storage services is protected, and you have to authorize yourselves typically against something like Kerberos in order to work with these services. And the second part is actually making Flink more secure by itself, meaning that all communication between Flink services, for example, should be authenticated and encrypted, that nobody can, sneak in a malicious task manager or job manager and try to grab data off your program, or just try to sniff data off the network. The most of this work has actually been contributed by AMC. That's a big thank you for that. It's a very important and a very tough feature. And if you're interested in some more of the details of what's actually happening there exactly, there's a talk tomorrow about Flink security enhancement, which goes into more details. Another area in which the community is working a lot is this area. I've found no better title than just to call it checkpoint save points. Maybe I should have called it continuous operations, because that's what it really is about. If you think of stream processing jobs as continuous processing job, the thing that's almost tautologically true about this is that they're continuous and should never be interrupted. And a lot of work in the last year went into building a sophisticated recovery model inside Flink that the system can always recover a job in the presence of failures. while maintaining high consistency. But what we've actually been seeing is that you can build an automatic recovery system that is as good as you want. There's always a pathological corner case when the system will not be able to recover itself, be that because maybe there's just a serious problem in the user's program that just prevents the system from making progress, that there's the division by zero or the time metric error, so that just causes the program to deterministically fail all the time. And that is not something that a framework can recover. Or maybe the cluster has gone so haywire that it will not be able to get new resources and recover. So what we're putting in place here are the tools that you can always forward recover a job into a new cluster, into a new program, and you'll have the tools to actually keep the program running. Another thing that may appear quite subtle, but it turns out it's actually quite hard and important, is backwards compatibility, not only for the APIs that was added in Flink 1.0, but for the application as a whole in the sense of backwards compatibility of the shape of the state of the application. So if you're writing a Flink application that is doing something slightly more complicated, chances are very good it's going to be a stateful application. It's going to keep Windows or some form of user-defined state. And that the API to access state is stable is one thing. The other thing is that if you actually have a save point that you use to migrate that to the new application, that newer versions of Flink understand this still. And while this may sound like, yeah, sure, why wouldn't it? It's actually kind of a tricky thing, because inside Flink, over time, the shape of how we represent state, how we manage state, evolves because of new features, new techniques going in to enhance performance or to allow for other features. So what this is actually adding is backwards compatibility for application state, if you wish. And one of the features that we're working on that has actually driven a complete rewrite about how Flink internally manages state is dynamic scaling. It may be the most requested feature in Flink right now. And I'm actually happy to see that most of this has actually entered the nightly builds already. Dynamic scaling is really all about making the stream processing more dynamic and more elastic, right? Over time, the throughput of streams, the available resources usually change, so you want to be able to adjust the number of resources that the stream processor takes over time. You want to just be able to shrink or grow the parallelism of certain operations. I think that's what it boils down to in the end. And while per se that doesn't sound so hard, it becomes actually quite a hard problem if you talk about stateful stream processing and exactly once guarantees. Because with all these changes of parallelism, it means that certain state has to be reorganized. It has to be reorganized in a consistent way. No introduction of a duplicate, no data loss at all. And that's kind of a hard problem to do that, at least if you want to do it efficiently. And yeah, this is one of the big threats that are happening right now and that are reaching conclusion and will be released in the next version. And there's actually also a talk with more details about that later tomorrow. One other area, so while this is kind of I think a very straightforward thing, a more subtle area but quite important, where we're currently working a lot, is the area of cluster management. So under this thread are a series of small modifications that all in all kind of reimagine the way that Flink integrates with other technologies in terms of using resources and scheduling. If you look at where Flink came from, the first parts of Flink are fairly old. It's the Stratosphere Research Project, started 2010. It started out as a standalone stream processor at some stream or batch processor. At some point, Yarn entered the picture. We tried to integrate Yarn, but the ecosystem has gotten more and more complicated. I've only listed like 4 ways that I've seen people running Flink: standalone, Yarn, on Mesos, or on Docker-based technologies. And the ecosystem is getting more and more complicated. So under this umbrella is a series of works that we're doing actually to make sure that Flink blends very naturally with all of these technologies. And the tough thing is there that actually all of them follow different paradigms. So the work to actually make it fit all of these paradigms is kind of like is a bit of a puzzling piece. How do you create blocks that you can best assemble so that you can fit all the shapes? That is also a piece of work that's driven by multiple players. The general rework of the cluster management is mostly driven by Alibaba and Data Artisans. The work on Mesos is mainly driven by EMC these days. There are also 2 more talks about more details if you're interested. First, running Flink everywhere is about the general reworking to make it fit more cluster managers. And there's a special talk just about Flink on Mesos. So yeah, this was a short glimpse at some of the threats in the areas of operations or blending in with infrastructure that the community is currently working on. Here's a thread that's in the category of opening it up to broader audiences, and I think it's actually fairly impressive what's happening in the area of Stream SQL right now. SQL is arguably the language that you would go for if, or the preferred language that you would go for if you want to open up this thing to an audience of non-programmers, people that understand the problem domains, that can think in terms of sets and streams, but don't necessarily want to program Java and Scala. And it seemed like every system in the big data space at some point, more sooner than later, actually said, yeah, of course, we gotta have SQL. In the streaming space, the situation is slightly more tricky because while SQL is a very well-defined standard and a very well-defined model, in the streaming space is not quite so clear yet. There exists something like a streaming extension for SQL, but it only covers kind of a few building blocks, and especially the semantics of how you deal with streams have gotten more elaborate in the last years. The time semantics, the windowing semantics, and so on, driven by, for example, suggestions like the data flow model and so on. All these are Stream SQL is far away from covering those. So I'm actually very happy to see that the Flink community and the Apache Calcite community, and as part of the Flink community, I count all those users like Alibaba and Huawei and so on, who are discussing on the mailing list and making suggestions. Hey, here's how we can actually find a good model for stream processing. I'm actually very happy to see that this is kind of it's a very active discussion that actually tries to come up with completely new models on how to suggest this. And there's actually a bunch of talks that have some notion of SQL in them at this conference. There's one mainly about just Stream SQL as a model, as a theory about duality between streams and tables and so on, later today. And even later today, there's a talk about how does Flink actually internally implement its relational APIs, that is SQL and the table API. Okay, so much for what is happening, what the community is working on right now. Let's look a little bit further of where could this whole space, where could Flink be going? And I'd like to talk about 2 things there. The first thing is, it's coming again, batch and streaming. And I promise I have a slightly different angle at this than last year. So I just want to repeat this to make it crystal clear. The separation of batch and streaming is one that has been technology-driven, not really use-case-driven, right? So it is, in most cases, quite artificial. And just to also point that out, because we've been basically talking just about stream processing here in this keynote, Flink is actually a fairly decent batch processor as well, and we see more and more users actually coming up and say, hey, can I actually use this for batch? Or users that just have been using it for batch for quite a while. And in fact, if you look at the program of this conference, there are a bunch of talks about batch processing. Let's quickly look at batch and streaming again. So with 2 data sources with continuous data over time, one above is, let's say, a log-based structure. I put in the Kafka logo here, but you could also think mapper streams or kinesis, anything that is like a continuous log of events. And below, a file system that has a bunch of files that, some form of rolling ingestion ingests. There is a file appearing every hour. My gut feeling is that a lot of people would still suggest the top one with streaming and the bottom one with batch. One is Kafka, the other is, let's say, HDFS or so. So the top one should be streaming, the bottom one is batch. It actually turns out that from the computational model, there's not a big difference between the 2. One is a low latency stream, the other is a high latency stream. If both of those are streams, then what is a batch actually? A batch is just that. It's a subset, a finite subset of the stream, right? So in some sense, a batch is really a stream that you give a beginning and an end. So far from the theoretical, from the use case perspective. why are people then actually using batch processors? If batch is so clearly just a finite stream, just a special case of streaming, why is anybody still using a dedicated batch processor? Or why is anybody still using Flink's dataset APIs? I mean, Flink is a common runtime for batch and streaming, which with sort of specialized instantiation of operators on the streaming side and on the batch side, slightly different APIs to make it feel natural on both sides. Why is that still there? Why do we actually have a dataset API still? Why isn't everything on data stream? And I think there are three main reasons why that is the case, where streaming has not completely caught up with batch yet. The first one is just a few missing primitives that are in batch processors or in Flink's batch API that are not in the streaming API. Some of the more straightforward ones are, you always have to do a window in the streaming API if you want to group over the entire thing. That is more or less just syntactic sugar, getting rid of that. A little bit more serious is what do you do if you actually want to do iterative computation? Graph algorithms, machine learning algorithms. The data stream API has some form of iteration, but it's an asynchronous iteration. It doesn't give you global synchronization, which makes a lot of these iterative algorithms much easier to think in if you have that. So something like a bulk synchronous parallel iteration is, for example, missing in the streaming API. The second and third part, resource elasticity and cost of fault tolerance, are kind of connected in the sense of batch processors still have, by the notion of having finite amount of work that you can chunk into these small units, they have a way of just getting cheaper fault tolerance and getting a more elastic way of processing, scheduling these small chunks in and out and so on more flexibly. But I believe that none of these issues is actually a completely fundamental one, right? I mean, the missing primitives are really just a matter of evolving the streaming API. And the cost of fault tolerance and accuracy and resource elasticity, Flink has a lot of code actually to make use of that in the dataset API. It does things slightly different in the data stream API, but I think there's a big potential in fusing those technologies, integrating them a little deeper to actually have batch and streaming unified, not just in the APIs, but throughout the entire stack. And I think that'd be fascinating because that is not really happening these days. If you look at technologies like Beam and the way it runs, for example, on Google Cloud, you see two completely different runtimes for streaming and batch, just because you still have these issues that are listed on this slide here. Having an engine that really can unify that throughout the stack, I think would be fairly impressive and innovative here. And that fact that Flink is on a good track to do this is I think we have a few proof points to actually say that Flink's on a very good track to do that. So these are from various blog posts and benchmarks, or from a presentation from last year's Flink Forward, where people did benchmarks of Flink for certain types of applications, both classical batch jobs like TerraSort, relational joins, and linear algebra and graph processing. And in all cases, it turns out it's actually a fairly good system for it. So much about the batch and streaming side. The other side that I would like to talk about is stateful stream processing. And to put this into context, let me take a minute to look at the history of what stateful stream processing went through over the last years. I would say if we just look at the Apache stream processing ecosystem here, you can already see this evolution. Storm was arguably the first system that provided an open source stream processor. It was built around the model of stateless streaming. It was sending events to different operators, and it would replay events on a failure to give you at least once message delivery. There was a little bit of support to, in Storm's higher level APIs to plug in some backing databases to keep some state, but it was never really a deep integration. So for better or worse, Storm just remained a stateless stream processor. That was the main reason, I think, why Apache Tzoumas actually saw some uptake when it came after Storm, because Tzoumas actually introduced the notion of state as a first-class citizen in the stream processor. But by its architecture and so on, what you could do with state in Tzoumas was a bit limited, and it didn't have exactly once guarantees, which a lot of people care about. So that, as Kostas mentioned, was what Flink then brought, the combination of accuracy, latency, and throughput. And if we look actually at this stateful stream processing, you know, when we worked on the first version of Flink's checkpointing algorithm for fault tolerance, I don't know for what reason, but I kind of had it in my head, yeah, of course, people are going to keep some counters and are going to be happy that the counters are persistent. Okay, that'd be a few bytes, maybe megabytes of state. That is what I guess people would use in stream processors. Turns out it's a lot more. I think by now we see certain jobs that keep tens of gigabytes per operator. Scale this over multiple operators and you come actually to a much larger scale. And we're already seeing people asking, you know, can we actually scale this to terabytes? Which is a bit of a crazy thing to do. But, I mean, the more you think about it, it's actually, there are pretty good reasons why this should be doable and what this could give you if you could actually do it, if you can scale the state in Flink to terabytes. Just two things here on the slide that I found are very good reasons to do that. One is a feature that's also entered Flink's nightly builds recently, queryable state, where you can actually just access the state in Flink's operators as if Flink were a database. And the second is a pattern that we're seeing a lot, that people that implement data-driven actions that take a lot of historic data into account. You know, an event comes representing a user doing something, and you want to take a lot of historic data into account to determine the action. You can just implement this as a special form of window or a special form of stream processor state. And if you take a lot of historic state into account, this is going to be a very large state. So how can we actually get there? How can we scale it to the terabytes? And I mean, not just be able to load this into the stream processor. That actually works today. The really tough thing is how do you make this very efficiently fault tolerant, this really large state, which has two sides, two dimensions. First, in some sense, how do we still do very fast and efficient checkpoints on terabytes of state? And how do you actually do very fast recovery when a machine goes down on that state? And without going into too many details, there's a general direction that I kind of see in this space happening, and that is, like, a lot of these questions have been sort of addressed in a different community before. How do you make large state and changes to large state persistent, right? The distributed systems community, the folks that have built key value stores like Cassandra and so on have actually spent a lot of work on answering these questions. And what I think is going to happen is that a lot of database technology is going to come into the stream processor ecosystem. There's going to be some form of convergence of these technologies. And I think there's a tremendous chance for stream processors here, because what we can actually see is that, similar to the way that the checkpointing algorithm that formed the basis, right? I mean, the checkpointing algorithm in Flink bears some form of resemblance of the Chandy-Lampert algorithm, but it can actually be changed and simplified because we have a more well-defined domain. And I think the same thing can happen here. A lot of the database technologies that are fairly complicated in the context of key value stores can actually be simplified when you put them into a stream processor and made even more efficient. And I think this is a very interesting thing that's about to happen. All right. I think with that we can conclude this talk. I hope you took away some interesting messages. I've listed 4 that you can quote if you slept through the keynote and you still want to tell people what it was all about. One thing is that we're really very happy to see that Flink is starting to run in some of the largest streaming setups that there are these days. And that the second thing is that we kind of see a shift in the focus of the community towards not only, here's the next application feature, here's the next cool way of doing windowing, here's the next way of, crossing this stream and that data set and so on. But a lot of features that just make it possible once you actually run this on a large scale or you run it in a demanding setting, that it actually keeps running and you're able to manage it. The last 2 things are going for a broader audience, mostly via Stream SQL, and then a little more forward-looking, the convergence of streaming and batch, not only on an application programming interface level, but also like on a backend, on a runtime level, as well as the stream processor becoming more and more not just a compute part of the infrastructure, but a part that actually owns a huge amount of the application state. Yeah, and with that, all I have to say is enjoy the conference, and yeah, we have a lot of good talks coming up, and a lot of smart folks here that like to talk about stream processing. So I hope you have 2 very good days. Thanks.